I'm Aisha B. Rahman. I'm the chair of IEEE Women in Engineering Albuquerque Section Affinity Group. I welcome you all to the monthly
Mhm.
public talk series of our Affinity Group. Today, as our guest speaker, we have Dr. Victoria Manfredi. And Dr. Victoria Manfredi is an assistant professor in the Department of Mathematics and Computer Science at Wesleyan University. She received her PhD and master's in computer science from the University of Massachusetts Amherst. I hope I said that correctly.
Yes.
Her BA in computer science and neuroscience from Smith College. Her current work focuses on characterizing wireless, mobile, and otherwise dynamic networks and using the derived insights to design more robust and private communication protocols. Today, she will be giving a talk on designing robust and adaptive routing strategies for networks. So thank you so much, Dr. Manfredi, for taking time out of your busy schedule to join us. We really, really appreciate it.
Wonderful.
Also today, joining us are our Affinity Group Vice Chair, Ariana Santa Maria Peñafiel, and our Affinity Group Advisor, Dr. Siropolo. Before
Mhm.
starting the session, I would like to ask Dr. Siropolo to say a few words on behalf of our Affinity Group.
Sure, thank you, Aisha. As we were saying earlier, before we start being recorded, we are a relatively small group, but we are quite dynamic. So we love to have speakers from the whole spectrum, from junior faculty to senior faculty, from industry, that they can share their experience and their research. It's very inspirational for our students, as they go through their graduate studies, and also we have few undergraduate students, and they can understand the challenges and what to expect from their future, but not only the difficulties, but also the positive aspects. And I appreciate it very much, Vicky, for being here today with us.
Sure. Well, thank you so much, Irene, for having invited me, and Aisha for organizing all of this. So, yes, shall I get started? Okay.
Yes, please.
First thing I was going to do was actually not talk about research. Let me make sure. But to sort of give you a little bit of an overview of how I ended up where I ended up. And though not shown on this slide, I actually, when I went to college, I was interested in chemistry. And that's not what happened. So actually, my father suggested I take some computer science courses, not because he thought I would do computer science, but because he thought it would be useful. And I think that's like generally really great advice for people, is to take some courses because it will be useful. And you might find that you really like it. So I ended up finding that actually those courses were more absorbing than other courses that I had taken. And I was lucky because, I was taking those courses at a women's college. And so all the students in the courses were women. And so my experience, I think, of computer science courses are a little bit different than a lot of women when they take courses. And then I got sort of lucky because I worked with a number of women professors as an undergrad on some research projects, two of which somehow back in the day involved reinforcement learning. And so this was sort of, I think, if you know anything about reinforcement learning, it started off, it had its heyday, and then it sort of became not that popular, and then it had its heyday again. And we're currently in the second heyday of reinforcement learning. And so I sort of got the tail end of the first heyday. And so there were, a couple of projects, including something that was my undergraduate thesis. So I had a professor, she was interested in reinforcement learning, she was really interested in jazz, and so we looked at jazz improvisation. And so that was the first project I worked on. And I was really interested in reinforcement learning in part because what I ended up studying as an undergrad was computer science and neuroscience. So like the neuroscience aspect of reinforcement learning, because at the time some of it was looking at sort of modeling how learning happens in the brain, was really, really, really interesting to me. And so I went to grad school and I'm like, I am doing reinforcement learning. That was my plan. And I found out I'm not actually as interested in the theory of reinforcement learning as I am interested in applying it to problems. And so that's something to keep in mind, is that, you know, sometimes you'll start off thinking you're interested in one thing, but you might find you're interested in something else. Or you might think you're really interested in something, and then it's not the hot thing to work on anymore, and you have to decide whether you keep working on it or whether you move to whatever else is hot. So for my PhD, I sort of started off looking at reinforcement learning. A little bit more on the theoretical side. I was less interested in that, and so I switched to networking and switched to a little bit looking at radar networks, and then looking more at routing. And so then I spent a lot of my PhD looking at routing problems, and I got really interested in routing, you know, and I really liked networks, and so I sort of stuck with that. And so I did my PhD at UMass Amherst, and then I ended up doing a postdoc at Boston University, working on some problems in routing that I thought were interesting, trying to understand, you know, when different kinds of routing strategies were useful. And then I went back to being more applied, and I worked at a company for a little bit, but I still did routing. But I started working on routing a little bit more broadly, so looking at routing not just in sort of mobile and wireless networks, but also routing on the internet, looking at how to circumvent censorship on the internet. But at that point, I sort of decided, you know, the problems are really interesting, but I wanted to be able to think more deeply about, you know, problems, and have a little bit more control over the problems that I worked on. And so then I went back to being faculty. And then I still worked on all sorts of routing problems, but then I also went back to reinforcement learning. And so it all sort of came full circle, and this is where I ended up now. So I don't know if we normally do questions in the middle. If there are questions, you can always, I guess, raise your hand and I will do my best to answer. So that was sort of the story of how I ended up at Wesleyan and how I ended up back doing reinforcement learning applied to problems in networks, which was not exactly where I thought I would start out, but actually where I ended up. Okay, so let me see if I rearrange the pictures here a second so it's out of the way. So I leave you with this. A lot of life is a lot like routing, because you have to make decisions about where to go, given sort of limited information about the network or the environment, your life as a whole, trying to get towards some destination. And let me see, why is this not visible? So I'd sort of leave you with a heuristic solution that, well, you know, you may not be able to optimize this perfectly, but as long as you're still learning new things and working with, you know, great people, it doesn't really matter. You'll end up somewhere interesting anyway. Okay. Okay. Let me move on. So the first thing, so how I sort of organized this was just talking about routing a little bit generally, and then talking about routing in one specific kind of network, and then talking about applying reinforcement learning to routing. Okay. So calling this the problem of getting from point A to point B. And this turns out is actually a very common problem. I have sort of here a little map of Middletown and Wesleyan University. And if you can sort of represent your data as a kind of graph, then this problem is important, even if you're not really thinking that you have a routing problem. And many things in the world can be represented as a graph or a network. And the first thing you might ask is, well, isn't this problem solved? You know, we use Google Maps all the time. We navigate, you know, what seems to be pretty well all the time. So it would seem like maybe this problem is solved. And that's a great question to ask, right? And so what I would say is, you know, it is solved in, you know, a number of cases, but then there are cases where it's not solved. And that tends to be true of a lot of things. So the first case you might consider is, well, whoops, oh, I'm going the wrong way here. Is that if there are a lot of people or packets or things competing for resources of that network, then the problem may not be solved. You may need to sort of consider trade-offs of who gets priority and so on, or or route suboptimally in some way. Or you may not have perfect information to route well. So that may also reduce, the performance of your routing strategy. There could also be an adversary watching the network, interfering with traffic in the network in some way. And so you have to consider, how do I modify my routing strategy to sort of navigate around this adversary, or hide my traffic patterns in such a way that the adversary, is not able to interfere or detect what I'm doing. It could be that the adversary is even more extreme and they're preventing access to different parts of the network. So then you have to be even more clever about how your protocols operate, whether you try tunneling traffic, in clever ways to other parts of the network and so on, trying to hide it from this adversary. And the last case, which is sort of the case that I have been thinking a lot about recently, is what if the network topology is changing over time, right? So how do you decide how to route if you have incomplete information about the state of the network and it's also changing, okay? And so this is what I was going to sort of focus most of this talk on, okay? Okay. And okay, so this takes us to the problem of routing in dynamic networks, as I have been calling it. So let me sort of set this up for you and see if we can, okay. So I want to think about a network where the topology is changing. So links may be appearing and disappearing between entities in the network, between devices, wireless devices in the network. Those devices may also be moving around. Okay? And those changes are going to be occurring both spatially. So different parts of the network may be experiencing different kinds of changes, and also temporally, so over time. And I want these changes to be happening, relatively quickly. Part of that is I'm not thinking so much about dynamics in terms of, like, let's say a social network where, yes, there will be changes, but it's happening at a somewhat slower time. So I'm thinking more about a mobile wireless network. And in real life, those networks do exist. Some of them, are military networks. Some of them are used for search and rescue. Some of those networks are used for robots. There's sort of things like the Internet of Things, and so on. A collaborator of mine works at Gotenna that builds these little devices that you can sort of associate with your phone to build a network with your friend, let's say if you're out hiking. And so these networks sort of have applications in areas where it's not easy to set up infrastructure to do the routing to get your traffic from one location in the network to another location in the network. So you might not be able to set up infrastructure because, let's say, there was a disaster, and so whatever infrastructure there is gone. It might be, some kind of war zone. It might also be, in other cases, maybe you just don't want your traffic going through, some kind of infrastructure that can be monitored by someone. You'd rather your traffic go through, a device of a person you trust in some other way. So this has applications in places where maybe there's censorship of some kind. Okay. And so the question is, in this kind of network, what does it mean to route? So what does it mean to get a packet for your data from one location in the network to another location? So for instance, here I have, you can think of these little circles, these little nodes as like wireless devices, and I put little arrows to show that they're moving around. And the dashed links are showing that, those two devices are within transmission range at that point in time. And so P is my packet hanging out at node V, and P has a decision to make of choosing a node to move to get closer to the destination and hopefully ultimately arrive at the destination. The thing is, P may need to go to some intermediate node, and have that node get it closer to the destination. It may not be able to just wait at V to wait until node V and node D are within transmission range. Okay, so if packet P is clever, it may decide that it's going to move to its neighbor U2. So it does that, it ends up at U2. That neighbor itself, U2, moves. And if we were really lucky, it ended up within transmission range of P's destination. Okay. And so then P arrives at its destination and everybody is happy. Of course, P might have made a different choice as it moved along. It might have moved to U1 and ended up farther away from D. Okay, and so part of the question is, how does P, what information does P use to sort of make these decisions? And how should it make these decisions? Okay. So making those decisions is generally quite difficult. Because that movement may not be known in advance, right? So you may be relying on things where you sort of may kind of know where they might be moving, but you may not know perfectly accurately, right? The opportunities, even when you're within transmission range of a device, those opportunities for communication might be quite limited. You may only have a small amount of time to exchange whatever information needs to be exchanged. Your routing strategy may need to do things differently in different parts of the network. So it may not be able to just, assume that the network has a particular connectivity. If you're trying to share, have different devices or nodes exchange information about the state of the network, you may find that it's hard to really get a good picture of like where nodes are and where they are expected to be, just because it takes a while to exchange information, because it takes time for information to propagate through the network. Okay. And then, there are different things you might be trying to optimize in the network. So, bandwidth can be quite limited, but also resources can be quite limited. You might have low energy or low power. So, and there's a general trade-off of, you could maximize the amount of stuff that gets delivered, but that would also incur, let's say, very high delay. Or you could try to reduce the delay, but that might reduce the amount of stuff that gets delivered, and so on. So it's not clear that there's, a perfect strategy. It's just a strategy that different strategies make different trade-offs. Okay. So sort of there's a couple of limitations that current, or let's say traditional approaches to routing these networks have. So one limitation is that they generally target specific kinds of network dynamics. So for instance, they may say, I'm going to assume that the network is generally very poorly connected. In which case, maybe I can sort of flood my packets through the network and I don't need to worry that, I'll waste too much bandwidth because we're so poorly connected that there won't be that much interference. Or it might be that, the network is very highly connected. Or it might be that links, last for a very long, connections stay stable for a very long period of time. In practice, though, you may end up with a mix of dynamics. So some parts of the network might be well connected. Other parts of the network may be poorly connected. The other limitation is that when we're sort of designing these algorithms, it's hard to figure out how to include really, diverse pieces of information. So there's all sorts of things we can measure about the network, but it's hard to decide how do you incorporate that into the algorithm. Like what, like for what values of node degree do I do, this kind of forwarding or routing? And so that is somewhat limiting because we have all this information, but we can't necessarily use it effectively. It's hard to decide how much to weight different pieces of information. Okay. So right now, there's not really a best routing strategy for mobile wireless network. And so an alternative is to say, what if we tried to learn how to route instead of trying to handcraft a strategy based on sort of our own intuition? Okay. And so this is what we're going to do. Okay. And this is, I decided to add what I'm calling just a little machine learning interlude, just to make sure that, in case people hadn't seen it, that we're sort of all on the same page and sort of motivate why, I ended up using reinforcement learning. Besides the fact that I really like reinforcement learning. Okay. So, machine learning is generally a way to have programs learn from data. And there's a bunch of different paradigms. Some of these paradigms have sort of a little bit of overlap. Broadly, whether we learn with a teacher or whether we learn without a teacher, or whether we have some way of interacting with an environment, but we don't have a teacher. And so one question to think about if you're deciding, well, I want to learn how to route, how do I decide how I should learn? Because you certainly could try to learn with a teacher in this. It's not that reinforcement learning is necessarily the best solution, right? So in some of the scenarios I'm thinking about, we don't necessarily have a teacher who can say, this is what would have been best, right? If we did enough work, maybe we could get that for some examples, but it's hard to get it for all examples, okay? We'd really like whatever learns to be able to generalize to other examples to sort of be able to pull out what is interesting and important itself, okay? And, and sort of this learning by interacting, which reinforcement learning does, is actually, I think, something that we sort of experience a lot in our lives. I think the classic example is learning how to ride a bike. That's sort of learning how to do many things. You sort of go through a trial and error approach to learning. So you sort of try it, and then it doesn't work, so you fall off the bike. And you say, okay, and you learn that actually the sequence of things that I did led to this bad event. And you sort of say, okay, let me change something about that sequence. And you try again, and then you refine. Okay. I mean, you probably did have somebody tell you, you put your feet on the pedals and sort of it works that way, but you didn't have somebody tell you you should apply like this amount of pressure and sort of angle yourself a particular way and sort of balance exactly one particular way on the bike. And so reinforcement learning sort of captures that, this idea that you're interacting with the environment and the environment gives you feedback. But that feedback isn't a teacher telling you what to do. That feedback is basically a teacher saying, you did well or you did poorly. Okay. Where generally this is just decision making under uncertainty. Okay. So if you haven't seen this before, the goal of reinforcement learning is really just to map situations to actions. So say, what is the best action for a given situation that will maximize not just my immediate, goodness, my immediate reward, but the expected return that I would expect to get if I take that action and see what happens after. So a lot of the applications that they have, a lot of game playing sort of fits nicely into this paradigm because the situation is sort of states of the game board, and you can give rewards on each step when an action is chosen, and you'll give sort of small rewards on time steps when you're just taking actions where nothing happens, and maybe a large reward when the game is finally won. And so over time, you learn to sort of propagate the reward backwards to figure out which actions actually led to the game being won versus being lost. And computer networks and routing, you can sort of have a similar thing happen. So you have a large reward when the packet is actually delivered. But then you get a small reward on other time steps. So to sort of give you an example in the routing case and what I mean by expected return. So going back to this packet P at node V, trying to get to destination D. So in the first time step, P gets this reward -1, right? In the next time step, it takes another action and it moves to U2, gets this other reward -2. And then it finally gets delivered, and let's say it gets a reward of 0. Okay. So the return that it got is the sum of these rewards until it got it to its destination. If the packet took a longer path to the destination, let's say it went to node, I don't know, W or U, then W, and so on before it got to D, then this reward, this total return will be smaller. Okay, so all this agent wants to do is sort of maximize its reward. Okay, yes.
So I just wanted to ask, when you say the reward, what do you mean by that?
So the reward is really just like it's like a number, right? It's sort of getting a bit of feedback that says this was good, this was not. So in every state, right, you take an action, you get a little bit of feedback saying, for this action in this state, you get this reward. Was it good or bad? So until you actually have the good thing happen, or until you sort of follow a path through these states and actions that gets you to your destination, you don't really get the good reward, right? And I think I have an example later, what reinforcement learning is doing. So you're basically taking these actions, you're getting these rewards, you're accumulating reward, and you're saying for this trajectory, I sort of got this return. For this other trajectory, I got this other return. But during learning, what will happen is you'll sort of propagate the rewards backwards through time. Because what I want to know is, I know, let's say here, if this packet moves to U2, on average, the expected return, the return that it will get after I take this action and follow whatever policy I would normally follow to the destination, on average, I get this amount of return. So let me see if I jump ahead slightly here. Because I think this will probably be clear if I actually formulate it, and then you should ask your question again. Okay. So if you think of this agent, in this case, this agent, let's say, is this packet. Okay, so you have this agent sitting in this state. Okay, so it is at this node with a network and some connectivity. And it's trying to decide its actions right now are, do I stay? Do I move to neighbor U2? Do I move to neighbor U1? Right? And what we want to do is sort of be able to assign, they call this a key value that says, this action will lead to this expected sum of future rewards in the future. So what you're trying to do is associate a value with this state action pair that tells you not just the goodness of what will happen immediately if you take that action, but what you think will happen eventually, right? So on average, after I take this action and I follow my policy, will I eventually end up at the destination in a short amount of time, or will I sometimes, take a really long amount of time? Okay. So this Q value is literally, it's the sum of rewards that resulted after I took that action. Okay, usually it's like the sum of discounted rewards because, you know, rewards you get further into the future are sort of usually considered less important than rewards that you got sort of immediately. And then if it's discounted also, then it ends up not being an infinite sum. Okay. Does that make sense? Okay.
Yes, I understood. Thank
Okay.
you.
It's a little bit of a weird concept when you first see it. So this Q value is just you're trying to capture, you know, all the things that could follow on from after you take this action in this state. And since, you know, multiple different trajectories could follow, it's an expectation over all those different trajectories because there's not just one trajectory. Yes.
So I had this question about something similar, like how would you formulate this reward function? Like, do you use the proximity to the neighboring nodes or maybe something else to formulate this reward function?
Yeah, so the reward function is actually, it's an interesting thing to formulate. It really affects how will you learn. So for instance, usually because reinforcement behaviors can be really clever. They can be like sort of a child that learns to do, you know, what you say you want to do, but not really what you want to do. It will just optimize the reward, right? So it'll be like, I will just do whatever maximizes the reward that I get. And so if you optimize it poorly, so you might have said, why do we have, like, why do it like this? Why have just like, you know, a reward when the packet is delivered, a really good reward when the packet is delivered, but not a good reward at intermediate time steps, like when it might have done something that's kind of good. The reason for that is it could learn to just get the intermediate reward. So you're trying to avoid it learning sort of doing something that will let it get a lot of reward without actually accomplishing what it's really trying to do. Okay.
Okay, so what would be a physical parameter in that case? Like what do you measure here so that you can ascertain that it should receive a positive reward or a negative reward? Like, is the packet being delivered considered something of a parameter here?
So right now, the only thing, this is not the reward function we use, but I'll show it to you in a little bit. But
okay.
Now the only thing that gets a reward of 0 is if the packet is delivered. If a packet stays at a node, so I'll tell you the reward function, if it stays at a node and does not move to another node, right now we give it a reward of -1. If a packet is transmitted, it gets a slightly more negative reward because that incurs energy and it gets a reward of -2. If a packet is dropped, it gets a really big negative reward.
All right. Yeah, I think I understand now. Yeah.
Does that make sense? Okay.
Yeah.
Okay, good. So you have a scenario where we're just trying to say, basically we're trying to sum everything that could happen after I take that action to that state into the single value, the single number, so that I can compare for different actions for the same state. Each of those state action pairs will have different Q values, and I will just take the state action, I will just take the action that has the highest Q value for that state. Okay. So, and what happens during training, so you can imagine that initially, if I were to list out sort of brute force all possible actions for each state, and then I'm just wandering in the environment, taking actions in different states, you know, I will have initialized these Q values, let's say randomly, if I'm not doing anything clever. So they're all initialized randomly. So initially, how good an action is in a state is completely unclear. But as I start taking actions for states, I start building up better estimates of how good they are. So they have this, you know, exploration-exploitation problem during training of sometimes you don't want to choose only the best action so far because it might not be a very good action because your Q values might not be that good. And then you sometimes do exploratory less good actions just to sort of experience what might happen. Okay. So you sort of have this sort of iteration of you take an action in a state based on its Q value. That impacts the environment in some way. It changes the environment. And so you transition to a new state and you get some reward. And then you do the same thing all over again. So you end up getting these sort of trajectories of like, in this state, I took this action, I got this reward, I moved to this next state. In that next state, I took this action, got that reward in that state. The Q value, let's say for action A in state S here, action A sub T in state S sub T, will end up being the sum of the rewards that followed on after I took this action in that state, right? If only one trajectory could ever happen after I did that, then this would be the Q value. But since, there's, with different probabilities, different trajectories could happen, there's sort of this weighted sum, this expectation over the different sequences of reward that might follow on after I took that action. Okay. And so then the question is, how do we sort of estimate these Q values in a sort of easy way? And there is, there are a lot of variations on this, but sort of the simplest rule is basically I take my current estimate of my Q value and I update it. So this alpha is just a learning rate to say how much. So my Q value is really the better estimate. The new estimate I have is the reward I just got in the current state plus the Q value of, this should be an A sub T plus 1, I think, the Q value of the next state I ended up in after I took that action. Okay, so this difference between the current Q value for that state, S sub T and A sub T, and the new estimate I have based on the reward I got and the best action in the next state and the Q value that I could have taken if I were really following my best policy, gives me sort of an error of like, well, this is the current value of the Q value I have. This is what is actually a better estimate. And so I take that the alpha just says, okay, well, let's take some of that error and update my current value to move that a little bit closer to the best estimate. Okay. And so if you iterate this and you do enough exploration, then eventually the Q value should converge, depending on the environment and so on that you're considering. And so you might say, oh, we're done, right? We're getting there, but we're not quite done, because I sort of describe this as, well, let's say we have a big table of like states and actions, and then for each action, each state, you look at all the possible actions, look at the associated Q values, and you say, I'll just take the best one. But of course, we could have many, many states and many, many actions, and having lookup tables of like, I don't know, millions or billions of Q values and trying to explore all those states and action pairs, wandering in the environment is going to really be hard to do. And so this is where all the excitement of like neural networks comes into play, because you can essentially use a neural network to approximate that mapping between the state action pair and the Q value. And so now you're saying, okay, well, I don't necessarily need to have this giant table, and I'll get a little bit of generalization. If I see this action, this state, maybe that will generalize a little bit, give me a little bit of insight into other actions and other states. Okay. Are there any questions on that? Oh. So that was sort of the machine learning interlude. Because what we're really interested in is doing this for sort of a mobile wireless kind of network, not just sort of my general environment. So in order to do that, that requires us to define states and actions and a reward function. Okay, the transition function will just be our environment, our network as it's operating, or our simulated network as it is operating. So when you start thinking about this, you have to start thinking, okay, well, who will be the agent? Will it be the network as a whole making decisions for everything happening in the network? Will it be devices making those decisions? Will it be packets making those decisions? Do I want to have some kind of centralized decision making or distributed decision making? You know, how do I define these states and actions for a dynamic network? What should the reward be? And then maybe you haven't thought about this, but also the question of how should we do training? Because if we try to train the RL agent online, you know, in the network as it's deployed, first of all, a lot of weird stuff is probably going to happen to people's traffic as that RL agent is learning the policy. And also, that network is probably also very computation and communication restricted anyway. It has limited bandwidth. And so we probably don't want to do that, but can we actually train offline in such a way that it's feasible to have that policy work properly when the network is actually operating? Okay. So what I'm going to do is just try to give you some insights into how we sort of did this. I'm not going to give you all the details, but I'll try to give you some of the key insights. Okay. And so the first thing that we actually spent a lot of time thinking about, you know, if you're a networking person and you're thinking about routing, it is the device that decides what happens to the packet, right? So in routing, the device, it takes the packet from, let's say, the front of the queue, it looks at the packet's destination, it looks up in whatever table and so on that it's using, the algorithm, and decides where that packet should go next based on the destination. This is complicated, though, for working with reinforcement learning, because the state of the device over time doesn't actually track what happens to the packet. Okay, so if I'm looking at what device, let's say device V here sees over time, it sees packet 1 passing through, and then it sees packet 2 passing through. So it makes it a little bit unclear how we design the reward function, for instance, for V, when it never really sees what happens to packets. Okay, so we sort of twisted around and said, actually, the device isn't going to be the one making decisions. It will be the packet making decisions. And so we will track what happens to the packet over time. And the packet state will be where the packet is currently in the network. And the actions are where the packet decides to move next. And then we'll define reward based on what happened to the packet. Okay. And of course, the packet will still be at a device. That device will still have the resources that the packet is using to make a decision and so on. The RL agent will be living at that device, but the decision making will be done and the learning will be done using sort of the packet point of view of things. Okay. So for instance, in the figure on the right, this packet P1, it chooses its next hop. So P1, the state of, let's say, P1's current state is V, right? It chooses to move to this neighbor, it gets some reward. It chooses to move again to the destination, gets some reward. Okay, so this actually makes it a lot clearer to follow what is happening to the packet over time. What is should be affecting the routing decision making over time. Okay, so in our implementation, in our approach, each packet is operating as an independent RL agent. Okay, so packets do not coordinate. Devices decide which packets get to make a decision, so they're still, pulling packets from the queue based on whatever queuing discipline is being used. Okay, and so they might be imposing some kind of fairness or something else on which packets get to make a decision. But once packets get a chance to decide where to move, they're operating sort of greedily for themselves based on whatever the reinforcement learning policy for routing that was learned. The next big thing was, if we were to do that, how do we define states and actions? So what features should be input into the neural network for the state, and what features should be input into the neural network for the action, so that we can get useful key values out. And the thing that we ended up doing was defining our features not in terms of particular devices, because we wanted to be able to learn a routing strategy that we learn in one network can learn in lots of I can still operate in lots of different networks with totally different connectivity. Okay. And so we ended up using sort of what we've been calling our relational features. So the features that we use don't describe, if a packet is at a device and it's trying to decide which neighbor to go to get to the destination, our features don't consider, this is neighbor 3 or neighbor, A with, our features are things like what is the distance between that neighbor and the destination versus my distance and the destination, right? Or what is my neighbor's node degree versus my node degree, to try to get some insight that is not node ID specific. Okay, so which means that if I sort of learn that neighbors that have small queue lengths and have short, let's say, delays or distances to my destination, that information, I can use that regardless of the network I'm in, right? So if I'm in a totally different network, but I see a neighbor with those features of like short queue length and small delay to destination, I can say, yes, actually, it still makes sense. You're still a good neighbor. I will still move, that packet will still move to that neighbor. Okay. So the features that we actually use, so remember, we're trying to define something to describe the state that the packet is seeing and the action that the packet is considering, so that the output of this network is sort of a Q value that says how good that action is for that state. Okay. And so the features that we sort of came up with here, so we have, for the state features, we have features that are a function of the packet. So things like the time to live, how many hops has that packet sort of traveled so far, the queue length at the current node that the packet is at, the queue length for packets going to the same destination of that as that packet, the node degree, the node density of that node. There's also some features that sort of summarize the neighborhood around that node that say, well, on average, how many neighbors do I have, right? Or on average, what is the average node degree of my neighbors? So for all the device features I have here, we sort of compute the min, mean, and max of those features over our neighborhood. Okay. One reason to do this is that if that sort of summarizes my neighborhood, and if I have only one neighbor, I can compute that. If I have 10 neighbors, I can compute that. So that means that if my connectivity is changing, I can still compute this. I can still use that feature. I don't have to change anything but the input into the neural network. I'm just changing, I just get different values for these features depending on my neighborhood. Okay. The actions themselves, the features for the actions, because our actions right now are just which node to move to, our action features are actually very similar to the state features. They're just features describing now not the node that the packet is currently at, but the node that the packet is considering moving to. So things like the same device features, but now about that neighbor. So what is the neighbor's queue length? Or what is the neighbor's queue length considering only packets going to the same destination as packet P? What is the neighbor's node degree? So on. Okay. Okay. And then, so that's sort of, so we start off with packets making the decision. We sort of ended up using these relational features to describe the states and the actions. So we have our states now, we have our actions, and then we ended up with, we now need to sort of define the reward function so we can actually do learning. And so this is actually what we ended up using was a reward function that I defined earlier. So we sort of define, we have 4 rewards here. So on actions, when if the packet moves to neighbor and is delivered, it gets a reward of 0 for that time step. If a packet decides to stay at the node that it's currently at, it gets a reward of -1. If a packet decides to be transmitted, it gets a reward that's a function of the stay reward. So for instance, we currently have alpha set to like 2. So the reward for being transmitted is -2, whereas the reward for staying is -1. So it gets a little bit of a penalty for moving. We don't want it to decide to just move too much because it's a little bit wasteful of bandwidth and so on. It may be unnecessary movement. If a packet is dropped, it basically gets the transmit reward for infinite time steps if you write out the sum and so on. Okay. And then we did a few experiments looking at how different rewards impact performance. And I think, unfortunately, I don't think I have the labels for these things here, but I can tell you. So this black dotted dashed dot line here is for when it's most, so it's, let me see if I remember here. So the red line is for when the transmit reward is -2. The black line here is for when the transmit reward is -10. So we really, really penalize forward. So the delay there is quite high, but the number of forwards, if you look on the right graph, is quite low. Yes.
So the reward is any negative penalty. It could be a penalty, and the highest reward is 0, which is if it gets delivered.
Yes. Yeah.
So is there any concept if it's getting delivered to the correct destination or not?
So it gets that reward when it's delivered to the correct destination. Yeah. So when I say delivery, I mean when it gets to the destination. Transmit, I think maybe is what you're thinking of, it moves to the neighbor.
Oh, okay. So the R transmit, which is also negative, is if it moves, but it didn't go to the destination.
That's right.
Okay,
that's right.
Okay. Okay. Thank you.
Yes.
So are these like plots for different values of alpha that you have considered in the simulation?
Yes, they're plots for different values of alpha. I don't know. I thought I had a little.
So we try to like determine alpha here experimentally, right? So I mean, we don't want too much movements, but we also don't want like way too less of movements, right? We want something.
Exactly. Like exactly. Yeah.
All right.
So we want to say, you could really, like, if you really, so part of this is saying is what is important for your network, right? If you really, don't want to move unnecessarily, then you really want to penalize during learning those transmissions, right? But if you care most about, delay, then, don't penalize the transmissions too much. What you actually see is, it's interesting because you see if the transmission, so certainly the delay when the transmit reward is the same as the stay reward, it's not that different from the red line, which is when the transmit reward is -2 and the stay reward is -1. But the number of forwards is quite different, right? It's like it has really no reason to stay versus move. And so it can move a lot. And it's sort of feels unnecessarily wasteful.
Right.
Yeah. Okay. Okay, so the last bit was, so I think it became pretty clear pretty soon, at least training the initial strategy while the network is in operation is not really feasible, just because there's too limited communication opportunities and so on. And also, if you go back to these rewards, what you see is that we need to be able to get that full trajectory of the packet moving around the network and arriving at a destination, right? And that's not something that's easy to get in a distributed way in a network that's operating, right? We need to know the path that packet took, when, the delivery, the reward, and so on. But that's very easy to record and train from offline. Okay, so that is what we ended up doing. And the relational features that we had defined actually made that pretty easy to do, because anything that was collected by any package could just all be recorded to the same file and used to train the RL agent. So we ended up sort of training offline, training based on all the data that was collected, training one RL agent. And then when we did our testing, each device sort of gets a copy of the RL agent, and then each packet, when it wants to make a decision, sort of independently uses that RL agent, basically the neural network, to make its decision. Okay. And that actually worked pretty well. There are, of course, some interesting things to consider in terms of like, what is the right sampling of the states and, in scenarios that you should see during training to generalize well. And so I think there's still some interesting questions there, but a lot of this training can actually be done offline. And then maybe there's some reason to do a little bit of updating online. I don't know, but if you've done a good sampling, it does seem like a lot of this can just be done offline. There were some additional considerations, which I sort of was trying not to go into too many details and get too carried away here. So one of the things that might have gotten glossed over a little bit here is that for an action, right, the number of actions you have at a node or at a device changes as a function of the number of neighbors that you have. Okay, because sometimes I might have 3 neighbors, and so I have a choice of staying or moving to each of my 3 neighbors, so that gives me 4 actions. Sometimes I might only have 2 neighbors, so then I only have 3 actions, either moving to one of those 2 neighbors or staying. And so a lot of the time what will happen is they'll say, well, we'll sort of make this state have each action that's possible here, and then have a list of Q values output for each of those actions in that state. That doesn't work for us, because the number of actions that we get in different states varies. So instead what we do is that we feed in the features for each action one at a time and get a Q value for each of those actions for those states, and then we compare the Q values. So we have to run that network actually multiple times. Yes?
So the layers that you are using in this neural network, they are all fully connected layers?
They're all fully connected layers. We have not done that much interesting exploration here.
Okay, so how many layers do you usually need for this to converge?
Now we have an input layer, we have this expansion layer, we have a compression layer, and then we have output.
Okay,
so only really 2 hidden layers. But
okay, all right.
There are lots of more interesting things to do there.
Yeah.
Okay. So let me I think there's one more. Oh, there's one other thing that's a little bit more subtle, is if you think of what can be happening in these networks. Suppose you're a packet, you're waiting in a queue. If you're not a packet at the front of the queue, oh, yes. Ask your question.
Sorry, I wanted to ask about the computational complexity of learning through RL versus using traditional routing protocols.
Oh, yeah. So on the plus side, we're doing this offline. If we were trying to do this online, I think a traditional routing protocol would certainly win, right? If we're comparing the online, compare it to a traditional routing protocol, in some sense, a traditional routing protocol would be exchanging information with its neighbors, possibly trying to collect state from multiple hops away in the network, right? In our case right now, we exchange information only with our neighbors. But then we do have to run the neural network, right? And so that probably does take a little bit more computation to do than like a traditional routing protocol. And we're running that neural network for each action that is chosen. And so then the question is, can we do better than a traditional routing protocol? Because otherwise it's a waste of computation and bandwidth and so on. Does that answer your question?
Yeah, I did. Thank you.
Yeah. Okay, so in the offline training, there's one more, I guess I'll just say there's sort of one more subtlety. Is a lot of time a packet does not have a chance to make a decision. And so it's sort of a waste of, during training, to sort of consider those time steps. And so you can actually use, they call them sort of extended time actions or options. Basically, they're multi-step actions. In our case, our options, our actions for the packets end up being options that sort of span multiple time steps, starting when the packet makes a decision and end right before the packet makes the next decision. So if the packet makes a decision, waits in a queue for a while, that's okay. We'll sort of compute the reward across that whole time period. And that actually speeds up learning. So it can sort of back up the reward across that whole time period a lot faster, or back up the return a lot faster. Okay, so that was sort of most of, like, those were sort of the main key ideas. And so what I was going to just briefly show you, okay, so I will wrap up quickly. So this just gives you some examples of different device movements, right? And so you can see this is just for 2 nodes. There's 100 nodes, or anywhere from 25 to 100 nodes in the network we're looking at, and this just shows you how they move over time. So like red is 1, the red solid line is 1, the blue dashed line is another node moving around. So the first one is a random waypoint. The second was this Gauss Markov model, and then we've been calling this last one. It's a Gauss Markov model with just a lot more variability in the movement. And so what and also just to give you a sense of the connectivity of these networks are a function of the transmission range. And so we explored a number of different transmission ranges for different number of nodes, varying from like 20 meters to 80 meters. And that sort of gave us a pretty good, going from poorly not well-connected networks to sort of very well-connected networks in what we were evaluating. The training we did, so we trained on 2 scenarios. One was a 25 node scenario with a transmission range of 50, so what I have circled in red here, for each of the random waypoint and the Gauss Markov scenarios. So those dots there were the training setting. We didn't train on the last scenario. But then what we did is we sort of evaluated the performance of the RL agents on a bunch of other settings. So for different numbers of nodes, so we trained on 25 nodes, 50 meters, but then we evaluated on 64 nodes and 100 nodes and so on, and many different transmission ranges. And what we saw is that it actually did a pretty good job in terms of delay compared to the other strategies, including some, really good strategies, this sort of seek and focus and strategy in black. So the delay was quite good and sometimes actually close to sort of the optimal, which is in gray. And the forwards were actually a lot fewer than, for instance, the black line, which was a more optimal strategy. And so we were actually able to generalize pretty well there. And so this scenario was just looking at training on the 25 node 50 meter random waypoint scenario and testing on the random waypoint mobility. And then we also did sort of some cross-model testing where we looked at the random waypoint trained RL agent and the Gauss Markov trained RL agent, and then looked at how well it did for the sort of the Gauss Markov Crowley scenario. And again, they were able to both do pretty well in terms of delay and sort of outperforming what we have considered sort of a pretty good routing strategy for those networks. Okay, so I think the takeaway that I wanted you guys to get is that you can actually sort of learn a strategy that generalizes. You can train offline, learn a strategy that generalizes to these different scenarios. I think there's more thinking and so on to be done, but it is possible to do. And if you're interested in more, reading and so on, there's a lot of links here. And that's all I have to say. You can ask me more questions, or you can go home. At least for me, it's 8 o'clock. So, yeah.
Actually,
Thank you
it
so
triggered
much.
a lot of the interest of the students. Usually we don't have so many questions, so we are really
Right. Excellent. Yeah. Yeah.
I just had one last question. So, when you're doing the mobility analysis, do you follow any particular pattern for the node's mobility?
Yes. Okay. So this is what I was. So we were using 3 different mobility models here, and so you can sort of see how the nodes are moving. So each of these points, I think decision points in terms of the mobility model itself. And if you see like this red triangle, I think that's the start. And there's like a red star where the node ended up. So you can think like a node is moving following this trajectory, or a node is moving following these kinds of trajectories. The parameter settings that we used for these models are in the paper. So I don't have those here. Yeah. And of course, there's lots of different mobility models we would like to look at, as well as sort of real mobility traces, just to get a sense of are our features really capturing what is important for making decisions.
Okay, thank you.
Yeah.
If anyone has any questions, I think you can raise your hand or use the chat. I think it's pretty late at your place, Dr. Manfredi. Yeah, so yeah, we can wrap it up if there's no
Okay.
more questions. And I want to thank you so much. It was a very interesting talk, to be honest, and I think I've learned a lot.
Okay, that is wonderful.
Thank you so much, Vicky, for taking the time. We appreciate it very much. You triggered a lot the interest of the students, and that's exciting. And we appreciate very much taking part of your time to present to this venue.
Okay, well, thank you guys so much for inviting me. And yes, and if you have more questions, you can always send me an email or something. So
Excellent. Thank you. Have a great evening.
thank you, everyone. Bye.
Thank you so much. Bye bye.